Everything you see right now is a lie, not a metaphor, not a philosophy, a scientific fact, the floor beneath your feet, the walls around you, your own hands. None of it is solid. None of it is what it appears to be. And the moment scientists looked deep enough inside the atom to find the truth, they wished they hadn't. Because what they found didn't just break the rules of physics, it broke the rules of reality itself. And the greatest mind of the 20th century, Richard Feynman, looked at all of it and said something that should genuinely disturb you. He said nobody understands this. Not fully, not even now. So what exactly is hiding inside the atom? Stay here, because the next 8 minutes will change the way you see everything. Let's start from the beginning. For thousands of years, humans believed that matter could be broken down into smaller and smaller pieces, until you reached something that couldn't be divided anymore. The ancient Greeks called this the atomos, meaning indivisible. And for a long time, that idea just sat there, a philosophical thought with no proof. Then in the 1800s, scientists started finding real evidence. John Dalton proposed that elements were made of atoms, and that different elements had different kinds of atoms. It was a revolution. Chemistry suddenly made sense. The periodic table started coming together. Everything felt organized, logical, almost beautiful in its simplicity. But science has a funny habit of pulling the rug out from under you just when you think you've figured something out. In 1897, a physicist named J.J. Thomson discovered something shocking. He found that atoms were not actually indivisible. There were smaller things inside them, tiny negatively charged particles we now call electrons. This completely changed the game. If atoms had electrons inside them, then atoms had structure. They weren't just tiny solid balls. They were something more complex. Thomson came up with a model he called the plum pudding model. Imagine a ball of positive charge, with electrons scattered through it like raisins in a pudding. It sounds a little funny now, but at the time, it was genuinely groundbreaking science. And it was only the beginning. Then came Ernest Rutherford. In 1911, just a few atoms thick, and he fired tiny, positively charged particles at it. His expectation was that the particles would pass straight through, but something completely unexpected happened, maybe bending just a little. Most particles did pass through, but some of them bounced straight back. Rutherford described it like firing artillery, shells at tissue paper and having them bounce back and hit you. He was stunned. After months of analysis, he realized what this meant. Atoms are mostly empty space. Almost all the mass of an atom is concentrated in a tiny, dense center of the nucleus. And the electrons? They orbit around this nucleus, far away like planets around a sun. The atom was not a solid ball. It was almost entirely nothing. Think about that for a second. You, sitting there right now, you are mostly empty space. The chair you're sitting on is mostly empty space. The entire physical world that feels so solid and real is almost completely empty. But here's where things get truly strange. Because even that model, the nucleus in the center, electrons orbiting around it, was not the full story. Scientists kept digging, and quantum mechanics started to emerge. And quantum mechanics doesn't just challenge your understanding of physics. It challenges your understanding of reality itself. One of the first things quantum mechanics tells you is that electrons don't actually orbit the nucleus like planets orbit the sun. That image is wrong. Electrons exist in what are called probability clouds. You cannot know exactly where an electron is at any given moment. You can only calculate the probability of finding it in a certain region of space. The electron doesn't have a precise location until you measure it. And when you measure it, it's not that you're discovering where it was, you are, in some sense, determining where it is. This is called the uncertainty principle, and it was described by Werner Heisenberg. And it's not a limitation of our measuring tools. It's a fundamental feature of reality. This is where Richard Feynman comes in. Feynman was one of the greatest physicists of the 20th century. He had a gift that very few scientists have. He could take the most mind-bending ideas in physics and explain them in a way that felt almost natural. Almost. Because even Feynman was honest about the fact that quantum mechanics defies human intuition at every turn. He developed a framework called quantum electrodynamics, QED, which describes how light and matter interact at the quantum level. And through his famous Feynman diagrams, he gave scientists a visual tool to calculate the behavior of particles. But more than his technical contributions, Feynman gave us something even more valuable: intellectual honesty. He looked at the strangeness of the quantum world and instead of trying to explain it away, he embraced it. He said this is just how the universe works, and we have to accept that, even if it makes no sense to our everyday minds. So what exactly is so strange about the quantum world? Let's go deeper. Inside the nucleus of an atom, you have protons and neutrons. Protons carry a positive charge, neutrons carry no charge. And for a long time, scientists thought protons and neutrons were. But then came particle accelerators. Fundamental, the smallest building blocks. Giant machines that smash particles together at incredible speeds. And when scientists smashed protons together, they found that protons themselves are made of even smaller particles, quarks. Quarks come in different types, whimsically named up, down, strange, charm, bottom, and top. Protons are made of 2 up quarks and 1 down quark. Neutrons are made of 2 down quarks and 1 up quark. And quarks are held together by particles called gluons, which carry what's known as the strong nuclear force. The force is called strong for a reason. It is the most powerful force in the known universe. And it has to be, because positively charged protons are all jammed together in the nucleus, repelling each other with enormous electromagnetic force. Without the strong force holding everything together, every atom in the universe would fly apart instantly. But quarks and gluons are not the end of the rabbit hole. Here's something that will genuinely shake you. In quantum field theory, the deepest and most accurate description of reality, we currently have particles are not actually tiny objects floating in space. They are excitations of fields. Imagine a vast invisible ocean that fills all of space. Now imagine disturbing that ocean, creating a ripple. That ripple is what we call a particle. An electron is not a tiny ball. It is a ripple in the electron field. A photon, a particle of light, is a ripple in the electromagnetic field. Every type of particle we know of corresponds to a quantum field that permeates all of space and time. And these fields are never completely still. Even in the coldest, emptiest region of space, quantum fields are always fluctuating, always vibrating, always creating temporary pairs of particles that pop into existence and then disappear almost instantly. This is called quantum vacuum fluctuation, and it has been experimentally confirmed. Empty space is not empty. It is alive with quantum activity. And then there is perhaps the strangest phenomenon of all, quantum entanglement. Einstein called it spooky action at a distance, and he hated it. He spent years trying to prove it couldn't be real. Here's what entanglement means. 2 particles can become entangled, linked, in such a way that the state of one particle is instantly correlated with the state of the other, no matter how far apart they are. You could have 2 entangled particles on opposite ends of the galaxy. Measure one of them and you instantly know something about the other, not because a signal traveled between them. Faster than light travel is still impossible, but because they share a quantum state that is, in some sense, beyond space. Einstein believed this proved that quantum mechanics was incomplete, that there must be hidden variables we haven't discovered yet. But in the 1960s, a physicist named John Bell came up with a mathematical test, and experiments based on that test have shown, repeatedly and conclusively, that entanglement is real. The universe is deeply, fundamentally connected in ways that our ordinary ideas about space and separation cannot fully capture. So where does all of this leave us? We started with the atom, something so small that millions of them could fit on the period at the end of this sentence. We went inside and found electrons, not orbiting like planets, but existing as probability clouds, their locations uncertain until the moment we look. We found a nucleus packed with protons and neutrons, held together by the most powerful force in the universe. We went deeper and found quarks held together by gluons. And then we found that none of these are really particles at all. They are ripples and invisible, fields that fill all of space. We found that empty space is not empty. We found that 2 particles can be connected across any distance. And we found, just as Feynman warned us, that the deeper you look, the less the universe resembles anything your mind was built to understand. And yet here is the beautiful part. All of this strangeness, all of this quantum weirdness, it works. Quantum mechanics is the most precisely tested theory in the history of science. It underlies the transistors in your phone, the lasers in your Bluetooth speaker, the MRI machines that save lives in hospitals. Every piece of modern technology you interact with every single day runs on principles that, at their core, make no intuitive sense whatsoever. The universe doesn't care whether it makes sense to us. It just keeps working beautifully and precisely, according to rules we are still only beginning to understand. Feynman was right, not just about quantum mechanics being strange. He was right that the willingness to sit with confusion, to not force the universe into a shape your brain finds comfortable, is the beginning of real understanding. The atom is not what you thought it was. Reality is not what you thought it was. And that is not a reason to feel lost. That is a reason to feel alive.